Signals and the classification of signals. A signal is a function representing a physical quantity or variable. Physical quantity or variable representation. And typically it contains information about the behavior or nature of the phenomenon. For instance, in a RC circuit, resistance capacitor circuit, the signal may represent the voltage across the capacitor or the current flowing in the resistor. Mathematically, a signal is represented as a function of an independent variable t. Usually, t represents time. Thus, a signal is denoted by x of t. Here, signal classification of signal, first one is a continuous time and second one is a discrete time signals. A signal x of t is a continuous time signal if t is a continuous variable. If t is a discrete variable, that is x of t is defined at discrete times. Then x of t is a discrete time signal since a discrete time signal is defined at discrete times. A discrete time signal is often identified as a sequence of numbers denoted by xn or xn, that is open parenthesis x base n. Here x of closed bracket inside n, where n is integer illustrations of a continuous time signal x of t and of a discrete time signal x of n are shown in figure. Here x of t mentioned in bracket, inside bracket t. Here square bracket, this one in discrete time. Okay, here x-axis time. Here x of t continuous time signal. This is the continuous time signal. Here discrete time signal is this one, x of n, x of n. In x-axis n minus 5, minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, 5, 6 up to n. Here x of n is in y-axis. Here 1, 2 up to x power. This is the discrete time signals. If you flat like this, so we got like this. Okay, then like this. Okay. Okay, so like this. So a discrete time signal x of n may represent a phenomenon for which the independent variable is inherently discrete. For me, instant the daily closing stock market average is by its nature a signal that evolves at discrete points in time. That is at the close of each day. On the other hand, a discrete time signal x of n may be obtained by sampling. Uh, a continuous time, a continuous time signal x of t, such as continuous time signals x of t not xt1 xtn, like this. So here x naught, here st1, here st. Yeah, in a shorter form, as a here also x of 0, x of 4, x of 1. So this x0, x1, x1. Where we understand that x of xn equal to x of n xtn xtn. This is for discrete time signal. This is for continuous time signal. Xn. Now xn are called samples. Xn are called samples. And the time interval between them is called sampling. The time interval between the sampling is called sampling interval. Time interval between them. This is a sampling. So here sampling. This sampling. When the sampling intervals are equal, uniform sampling, then when the sampling intervals are equal, uniform sampling. If the sampling interval is equal, then that uniform sampling. You can say uniform sampling. Then xn equal to x of n equal to x of nts, where ts is the constant, is the sampling interval. This is the sampling interval, so constant. Okay, this is the number of how much. Yeah. A discrete time signal xn can be defined in two ways. We can specify a rule for calculating the nth value of the sequence. For example, uh, x of n equal to xn equal to 1 by 2. Condition is 1 by 2 power n equal to n is greater than 0. This is the answer. If n is less than 0, then 0 answer. This is n is greater than 0 or equal to 0. So 1 by 2 power 1 by 2 power n. This is the xn, x of n. We can also we can specify rule for calculating nth value of the sequence. Nth value of the sequence. Okay. We can also explicitly list the values of the sequence. For example, the sequence is shown in figure B can be written as xn equal to 0 0 1 2 2 1 0 1 0 2 0 0. Okay. Here xn this is 1, this one. So from here we have to take xn. We use the arrow denote the n equal to 0. Here is n equal to 0. That we shall use the convention that if no arrow is indicated, then the first term corresponds n equal to 0, and all the values of the sequence are 0. Yeah, sequence are 0 for n is less than 0. The sum and product of two sequences are defined as follows. The sum and product of two sequences. The sum and product of two sequences are defined as follows. Cn an plus Pn, Cn equal to n plus Pn. Cn, the sum and product of two sequences. Sum and product of, this is the two sequences, an Pn. This is a summing. Here sum. Product is here an into Pn. Pn. And then here Cn alpha of an. Cn alpha of an. Alpha is the constant. Analog and digital signals. If a continuous time signal x of t can take any value in the continuous interval a to b, where a may be minus infinity, b may be plus infinity, then the continuous time signal x of t is called an analog time signal. If a discrete time signal x of n can take an only a finite number of distinct values, then we call this signal a digital signal. real and complex signals. A signal A signal x of t is a real signal if its value is real number, and a signal x of t is a complex signal if its value is complex number. That is, a signal x of t is a real signal if its value is real number. If its value is real number, real signal. And if x of t is a complex signal, if the value is a uh, uh, complex number. The y is complex number, then x of t is a complex signal. Complex number, complex signal. Real number, real signal. A general complex signal x of t is a function of the form x of t equal to x1 of t plus j x of x2 of t. In general, complex signal x of t is a function complex. Okay, complex, where x1 of t and x2 of t are the real signals. X1 of t, x2 of t, okay, real signal. Okay. And the j equal to root of minus 1. J equal to root of minus 1. This is the root of minus 1. Note the equation 1.1 t represents t, the t represents either a continuous or time signal. Continuous or a discrete variable. Sorry, yeah, continuous or discrete variable. This determined deterministic and random signals. Deterministic and random signals. Deterministic signals are those signals whose values are completely specified for any given time. Deterministic signals are those signals whose values are completely specified for any given time. Thus, a deterministic signal can be modeled. Deterministic signal can be modeled by known function of time t. Known function of time d. Modeled. Okay. Random signals are those signals that take random values. Random signals take random values at any given time, must be characterized statistically. Statistically, random signals will not be discussed in this text. Even and odd signals. A signal x of t or x of n is referred to as a even signal if condition means condition if x of minus t equal to x of. It means this time is negative also, but that equal to x of t. It means even signal. Like this, say x of minus n equal to x of n. Here, if not coming negative, then even signal. A signal x of t or x of n. This one is for continuous, this one for discrete. Referred to as an odd signal. This one for even signal, this one for odd signal. When the same x of minus t equal to that same signal, same sign if it is coming, then odd signal. Here also same x of minus n coming to minus x of n. X of minus t coming to here minus x of t. That this is the odd signal. When negative only same here, positive is nothing matter. If